Good morning. Welcome to Krishna's classroom. Today we explore a new type of convergence. Recall that we had been looking at the convergence problem in this context, namely that our problem is this: you have a sequence Fn which converges to F. In some way, I'll list out the sort of things that. Okay? Then the question that you are asking is this: integral can you say this? It essentially means that you can interchange the integration and the limiting process, because f is essentially limit n tending to infinity of f. Okay, right. Now, what sort of convergence we have already handled? We have looked at the following types of convergence. One, uniform convergence. Two, point-wise convergence. Now, slowly the measure is getting reflected in the next one. Point-wise convergence. Almost everywhere. That means except on a set of measure 0. Then now we are going to introduce a new type of convergence. The fourth one that we are going to introduce is so the theme of this talk is the concept of convergence in measure and trying to understand what it is and what are the consequences from it. Okay. So these three we have considered, and you know that you have uniform convergence, then point-wise convergence is assured. You have point-wise convergence. Point-wise convergence, almost everything, everywhere is assured. Okay. So you have this. This implies, and so on. Okay. Right. Now, what we are going to do is look at the new concept of convergence, which involves measure in a big way, and then relate it to the other types of convergence and explore this. Okay. So let us first look at what it is all about. Okay, let me draw a diagram. Suppose this is the E, and you have f. I have drawn as a continuous function, the graph of a continuous function, and now I have a sequence of functions fn, which probably having some form like this. So let me use another color to mark this. So fn is something this is you have a sequence of such functions. Now what we are trying to say is this: whether this fn x for each x goes to fx. This is something that we want to explore. Okay? Or fn converges to f in some sense. A sense in which we want to do is what it says is that suppose you demark a road, so this is a road around f. Okay, so this is what you call fn minus what you call a some number eta. So this is fn f plus eta. This is f minus. So f lies between f plus eta and f minus eta. That means for each x, fx lies between. So this is what you have. Eta positive. So where does this fn enter this region? Okay. Right. So if you look at this portion, this is the portion in which fn enters this region. This portion, as well as you can see this in our figure, this region as well as this region. Okay, this is where fn, the graph of fn lies inside this road. Outside that it doesn't. Okay, so you have a region. Now these portions are where mod fn x minus is greater than what we want to assert is the following. As n gets large, because you are given a sequence fn. Okay, so you have the sequence fn. As n gets large, okay, what happens is, suppose fn is converging to f at all points, then what would happen? What would happen is that at some stage or other, fn x for a given x, fn x would be satisfying this condition. Okay, so fn x is going to be less than or equal to, so this is what you have. So you will have fn x minus fx will be less than okay. So you see that the complement of this, that means the region where fn x minus fx greater than eta will be this portion that I have marked. Okay. So if Fn converges to F, what happens is that the length of the region on which this is greater than eta as n becomes large will be increasing. Okay, right? That, sorry, will be decreasing, because what happens is that the I said wrongly. Suppose this is Fn plus 1, then you see that Fn plus 1, the corresponding region is going to be smaller. Okay, so more and more of these Fn's will be entering this road. Okay, that means the measure of the set on which Fnx minus Fx is greater than eta will be going down to 0. Okay, right? That means from some stage onwards, all these Fn's for each x, you see Fnx to the difference between Fnx and Fx will be greater than eta, then such set is going to be, such set of points would have measure 0. So let us now formulate the definition properly. So I hope you have understood this. Now you can make this analysis and have a look at it. So we will define what is called convergence. Let Fn be a sequence of measurable functions on a measurable subset E R and F a measurable function. Let F and each Fn be finite almost everywhere on, that means except possibly on a set of measure 0, this is going to be finite. The sequence Fn is said to converge in measure set to converge in measure to F if provided for each eta positive limit n tending to infinity of the measure of the set of all x belonging to E, where Fn x so this is a subset of E, okay, and this is the subset on which Fnx and Fx differ by more than the given eta. So you fix an eta or you take an eta, then for that eta positive, you look at the set of all x belonging to E for which Fnx minus Fx greater than eta. Then what happens is, suppose Fn is converging to F, that means Fn gets closer and closer to F. What happens is, as n becomes large, you see, it enters this road surrounding F. Okay, this enters the road surrounding F. Now, what happens is that, so it leaves, that is, more and more points to enter this road. So you are looking at the measure of the left out portions. That means the points where it does not enter the road. Okay, so we suppose the measure of this goes to 0 as n tends to infinity, then you say that Fn converges to F in measure. Okay, so for each eta positive this should happen, then you say converges in measure. Now this idea, I think you'll have to look at very closely, and maybe when we look at some example, it will be clear that what kind of complexities can arise. We will later consider an example. For instance, you can look at this, compute this. Look at Fn x you define as x to the power n over the interval 0 to 1. Okay. Now, you can actually draw some pictures and make some computations. Because what happens is this. Let me keep this figure for the moment. Okay. Then let's try to work it. Now, what happens is, if you look at this, see what you have is this. See, this is your F1. F2 is this. Okay, and so on. So Fn 1. Then you see that at each x lying between 0 and 1, that means x belonging to Fn x converges to 0. Okay. Now you can all say that Fn x converges to 0 in measure. What to do? See, you take an eta. So then this is the one. Now you see that the Fn minus 0 is less than eta on this portion. So here Fn minus eta, Fn minus f is 0, is less than, and on this portion greater than or equal. This is your eta that you. Then what happens is, for each n eta you have this kind of thing, and for each fn this happens. And now see, as n increases, the fn becomes flat. So more and more flat. Something like this. Okay. So you can show that, actually compute and show that you are talking about the measure of this particular interval for a fixed eta. What happens to that? That is something that you have to look at. So as n tends to infinity, you can show that the measure of this actually goes to 0. Now you see that at 1, it takes all these functions take the value 1. Therefore, the function converges to 0 on the interval 0 to 1, and at 1 it converges to 1. Okay, but then you can easily see that if you apply this definition, it converges in measure to 0. So that's an example. Now we make some remarks. It's a good example. Some insight. Now do some computations that will tell you what is the interval on which this stays closer to 0 within eta, and you can work out this actually. Okay. Now we make some remarks. When we write Fn converges to F, then we implicitly assume Fn and F are now one of the immediate consequences is this. Second remark, is that if uniformly on E and F is a real valued measurable function, function if then converges to f or in other words what you are saying is that if Fn converges to F uniformly, then Fn converges to F in F. So uniform convergence, or in short, this is what you have. You know that uniform convergence is a very strong form of convergence. Therefore, you naturally expect such things to happen. We already know that uniform convergence uniform convergence implies convergence pointwise, and also naturally convergence pointwise almost every. That's a less relaxed form of. Okay, so but the converse of these things are not true, because if a function converges, if a sequence converges pointwise almost everywhere, it does not mean that it converges everywhere. Okay, pointwise. So even if it converges pointwise everywhere, it may not be uniform convergence. Okay, so all these things we have already seen. Now we are now bringing in a fourth type of convergence into the picture and trying to explore the interrelationship between these types of convergence. Okay. So what next? Let us try to explore the proof of this. It's quite easy to prove this because you have proof of this remark. Convergence. So Fn converges to F uniform. Such that an epsilon so this is the uniform convergence. This is what the uniform convergence means. Now you see that what happens to the set where Fnx is greater than minus Fx is greater than epsilon. So look at the set. So you see that for all n greater than n, you see that this is less than epsilon. Therefore, what you have is that what happens is that for every n epsilon has, now this set is equal to E. Okay, this is what you have. What does this mean? This implies that for every epsilon positive, for each epsilon positive, the set no, sorry, this is empty. This is what this is empty. Okay, therefore, for every epsilon positive, has which implies so this is true. So for each epsilon you can get this. What does it mean? It means that this becomes the measure of this becomes this goes to 0. Okay, fine. So naturally you ask, suppose you relax this criteria of uniform convergence into point-wise convergence. Can you say whether the same result would hold? So let us explore this. So the question that you take up next is this. Suppose we replace uniform convergence by point-wise convergence almost. Is the result, namely measure. Now this is the question that you are asking. Suppose I replace this uniform convergence by point-wise convergence almost. Is this, can you assert that this is true? This is the question that you are asking. Now in this context you see that you need some kind of restrictions on this. First of all, we would need to clamp a restriction like E has finite measure. If E has finite measure, then you can say that F1 converges to F almost everywhere implies, pointwise almost everywhere implies it converges in measure. Okay, so let us write down the theorem. So the answer to this is this: yes, if this is the answer. So we are going to state the theorem. This theorem is assume E has finite measure. Let of measurable functions on E that converges to pointwise almost everywhere on E and almost everywhere on it. Then in measure on. So the only condition that we need is that the measure of E is finite. Then pointwise convergence almost everywhere also implies convergence in measure. Okay. Proof is not very difficult. Okay. So let us prove this theorem. First of all, we observe that f is being the limit of pointwise limit of almost everywhere of measurable functions fn and that's a consequence of an earlier result which we have proved. Pointwise convergence the limiting function is also measurable. Now let us try to arrive at the conclusion of the definition. That is, Fn converges to F measure. So let eta positive let epsilon be positive. Then we seek an index n such that measure of the set of all x belonging greater than eta less than epsilon for every n. If you can prove this, then of course you would have concluded that Fnx converges to Fx. Sorry, you would have concluded that this limit of as n tends to infinity of this is equal to 0. Now we apply Agraff's theorem. Just recall the result. There exists a measurable subset F containing E with measure of epsilon such that Fn converges to uniformly on F. What we have proved is that the pointwise convergence of Fn to F is nearly uniform convergence. This is the content of the Agraff's theorem. Okay, so that nearly factor is coming here because there is a subset, measurable subset F of E such that on the complement of F in E, the measure of that set is less than epsilon, and on F the sequence Fn converges uniformly to F. Which implies there exists n such that for all n greater than n. For every n because you have uniform convergence. Okay. Thus for n greater than or equal to n, the set of all x belonging to E on which greater than eta is a subset of because on the entire f you are going to have this less than epsilon for all n greater than some particular n. Okay. What does this mean? We also have from Egor's theorem that measure of this is less than epsilon. Therefore, okay, that is converges in measure now you see that this is an important factor, that is if E is not a finite measure, for instance on the whole interval R or on a half interval 0 to infinity something, then what happens is if you take a subset of finite measure from it, okay, like f, then the complement of that will have infinite measure. So you cannot write this part at all because E slash f is not necessarily a finite measure. Okay, therefore, see that you cannot make the statement. So we make a remark. So this completes the proof of it. Above theorem and that's one conclusion. The second conclusion is the following. The converse of this theorem is not true. The converse of what will be the converse of this theorem? Suppose Fn converges to F in measure, then even on a set of finite measure, you cannot say that Fn converges to F pointwise almost everywhere. So that is not true. Okay, that is need not imply pointwise almost everywhere. Okay, so let us look at an example to substantiate this point. So you look at the following example. It's an interesting example. You take E as 0, 1. Now we take subintervals In infinity So you take the interval 0, 1. So this you can call I naught or something like that. Okay. Then you have, what you do is you divide this into two parts. So you write interval 0, half and then you have 0, 1/3, 1/3 to 2/3, 2/3 to 1. That means you split this into three equal parts. And then eventually, the kth step would be to divide this into 0 to 1 by k, 1 by k to 2 by k, and so on. The last one is going to be k minus 1 by k to 1. And so on for. So this is going to be the breakup of 0 to 1. Make it in this way. Okay. So INs are going to be, this is going to be I1, I2, I3, I4, I5, I6, I7, IA, and so on. You choose in that order. Okay. So this is the kth step. This is the third step. This is the second step. Now this is the first step. Okay, so I hope you understood the breakup and how IN comes. You don't need too much of thinking on this. See, now we construct our functions Fn. That's our task next. So let us construct Fn for each n define Fn to be the restriction of the characteristic function of I on E. That means you have equal to 1 when x belonging to In, and this is equal to 0 x belonging to that is a definition. That's your reference. Now what we claim is that okay, so what we do is we have let's say what f is, and let so that is f identically equal to 0. Now what we claim is this. Okay, what can you say about this IN? IN is going to be in one of these batches, say for M. Okay, suppose IN belongs to the collection it has to be for some M there. It is going to be in one of these for some M. That is given N, there is some N M such that IN belongs to this collection. Then what you have is length of IN is going to be equal to 1 by so that As n goes to infinity, m also goes to infinity. Okay, limit n tending to infinity, which is the measure of in, because together. That's the reason. Now, for to choose a eta that lies between 0 and 1, because beyond that is irrelevant. Okay, right? Because all the INs are bound by 1. So all the FNs are bound by C. Takes only 2 values, and F is also identically equal to 0. So only eta less than 1 or eta that lies between 0 and 1 makes any sense. Then for this, you see that you get the x belonging to E, for which eta, this is contained in some IN. Okay, certainly it is contained in IN, that's clear, right? Because the only points where Fn is going to be greater than 0 is outside the particular IN that you have. Okay, right? And therefore 0 is less than or equal to measure of C. So you have the result for any eta that lies between 0 and 1, you see that this is going to happen. Therefore, now it is clear that, so what we conclude is that Fn converges to F in measure. That is clear. So we have got a sequence that converges in measure. But what we claim next is that at no point this sequence converges to 0. That's a startling thing. See? Why it is so? Let us examine it. That's quite easy to see. Now you see, you look at this one, F1. Sorry. Working on the interval 0. Okay. Everywhere there it is 1. Okay. Now, let me mark this. F1 equal to 1. That is the value. Now, what about this? F2 is 1 here and 0. This is F. What about F3? F3 is 0 here and 1 here. This is the state of F3. This is F1, F2, F3. What about F4? F4 see, F4 is 1 here, 0 here, 0 here. F5 is again 0 here, 1 here, 0 here. What about F6? F6 is going to be, I'm just trying to give you an idea. See, the F6 is again a breakup of the same kind, and it is 0 here. This is F4, F5, F6. 0 here, 0 here, 1 here. 1 over here. Now you take any x. What happens? What is the sequence? Suppose x is here. What is the sequence that is emerging? To see that, it is going to be 1, 1, then 0, then possibly 1, depending on where it is, 1, and then 0, and so on. So it is going to be 0, 1, 0, 1 appearing somewhere. So what happens is, if you take the tail of this sequence, it is not going to be 0. Okay? You cannot say that after some stage, Fn is going to be 0 at a given x. Okay? What happens is, again somewhere that 1 will be appearing. Okay? So, at no x belonging to Fnx is not 0, some n greater than particular n. This is not there, because what happens is again 1 will be appearing, so because you are going for this subdivision, so it's clear that it's going to be Again 1, probably 1, 0 you are taking here, or here if you are taking, then it's going to be 1, 0, etc., etc. But what happens is in between, that one start entering at some stage. So it's not going to be, the tail of the sequence is not going to be 0. Therefore, it doesn't converge. So the tail not x belongs to. What is the consequence? So fnx does not converge to 0 at any for any x. However, fn converges to f in measure. So that of course shows it clearly that you cannot write down the converse of the result that we have used. Okay, and I think that's a nice place to stop. Now we explore this problem further, and eventually what we want to look at is the whether interchange of integration and limiting process is feasible. Okay, so thank you very much. I will come back with the continuation of this in my next lecture. Thank you.